Good evening, class. Hello, my name is Titi, and today I'm here for my week 7 oral presentation. All right. To start with, thank you for listening to my presentation here in week 7. I've had a great time with this class, enjoyed it. And now I'm gonna get into the project, right? So my project is the use of artificial intelligence (AI). Is how does it predict the likelihood and severity of seasonal droughts across the United States, right? Drought impacts of water supply, agriculture, wildfires, and ecosystems and economies can be largely affected by droughts, right? With accurate seasonal predictions made a few months in advance, we can help managers, water supply managers, farmers, and emergency planners and policymakers to make better decisions with that, right? My goal is to build a model where that it produces and provides a useful lead time while being transparent, and also the model cannot be claimed. Number 2 in this part of my project is, where is the teleconnection and feedback idea in my proposal, and what does chapter 4 section support about it, right? So the teleconnection is my proposal as the large scale of climate patterns in the Pacific Ocean, such as the ENSO and the Pacific Decadal Oscillation, and influence moisture transportation participation over North America. And then with the effect of soil moisture and drought conditions in the western US, in chapter 4, section 4.2, the teleconnections, the text explains that energy and water are connected across long distances through atmosphere, oceans, this creating relationships between the distant regions. This section supports the idea that the offshore and climate variability cannot be linked to the drought on land. Moving on to the part 3 now. What data are we using, and why does the data fit your question? I'm using the combination of climate, hydrochloric, and land surface data. All right, so we got the NOAA, Climate Prediction Center, and data ENSO as well, on a PDO index, as well as the sea surface temperatures, SSTs. We have a reanalysis data from ERAF, right? We have as well precipitation and temperature and geopotential and high humidity, and then as well as wind. We have soil moisture data from NASA and SMAP. We have drought observation from the US Drought Monitor, and SPEI, the Standardized Precipitation Environment Transportation Index. There we go. Right, so these data fit my question because they capture both the large-scale climate drivers, the teleconnections, and the local land surfaces and the contribution to the droughts. They also span many years, which allows the model to be learned from different drought and non-drought seasons. Right, so for me, what AI method are we using and what baseline could we compare it to? Right, so I will use a machine that called the Random Forest ARF. The Random Forest can capture non-linear relationships between interactions between many variables, right, which is important for a complex system. A system like drought, especially how complex it is, predictions we haven't had a chance to obviously grab a hold of it properly. I'll compare the RF to the model to a baseline model, like a multiple linear regression one. This baseline basically uses the same predictor and variables and assumes linear relationships. Comparing this to the simpler model helps us see whether or not the added complexity of the random forest actually improves the predictions or not. Now moving on to the correlation versus caution, right? What can your model claim, and what can it do not to claim? Obviously references from section 4.1 from chapter 4. The correlation versus causation. The text explains that the correlation does not imply causation in the Earth system because many variables are interconnected. My model can claim that certain climate patterns are statistically associated with a drought occurrence or severity. It also estimates the likelihood of drought given the current conditions that we have. However, it cannot claim that specific climate drivers causes drought. For example, even if the ENSO is strongly correlated with drought and in my model per se, that does not prove that ENSO causes droughts. Other factors like land use and groundwater or internal climate variability may also play important roles. So my conclusions say that will be about relationships and predictive skills, and this will not be a cause or an effect. How will we check results, and how are they just not accidental correlations? We will use several steps, right? We have a train test split where our train models on the earlier years and test on later years. The model has never seen. right? Cross-validation. I will use K4 cross-validation within the training group period to reduce overfitting. And then we have another one, multiple metrics. I will evaluate use and accuracy for jar occurrences, RMSE, and then we have MAIE for jar severity as well. And then we have feature importance and severity tests. I'll check whether the model relies on physical, or does it rely on physical resemblance or driver's driver. Moving on now to my conclusion. In summary, basically, my project will use AI to predict seasonal drought by linking large-scale climatic connections to regional drought outcomes. Especially grounded in Chapter 4, Section 4.1, they talk about the correlation versus causation, where the teleconnections obviously are heavily linked to that. I will build a model that is obviously based on evaluated and carefully been put up against the baselines for how robust it is. We'll test for that robustness as well. The goal is to obviously provide a reliable and ethical, actionable, and predictable system that obviously can help the community prepare for droughts way better. Thank you so much for listening to my presentation.